A radio operator sends a position. It is accurate, it is received, and it is useless. 95 people are aboard a brand new ship built to survive ice, 65 kilometers south of Cape Farewell in a January gale, and nothing on Earth can reach them in time. The Hans Hedtoft was never found. One life ring came ashore in Iceland. People assume the Labrador Sea kills because Arctic ice meets Atlantic storms. True, and almost meaningless. The killer is the warm water underneath the cold air. Basque whalers, wartime pilots, and weather ship crews all met a version of the same thing. Look at where that ship went down, and you start to understand the geometry of the problem. The Labrador Sea is a wedge of open ocean, roughly 1,000 kilometers across, pinched between the coast of Labrador on one side and the southwest coast of Greenland on the other, closing to the north at Davis Strait and opening to the south into the full North Atlantic. On a map, it looks manageable. It looks like a bay. It is not a bay. The central basin drops past 3,000 meters and in places goes beyond 4,000. And between the two continental shelves, there is a stretch of deep water several hundred kilometers wide where there is no island, no headland, no shoal, no bank, and nothing at all to break a sea once it starts running. That single fact does more damage than any statistic about wind speed. In most dangerous waters, the danger comes with an escape clause. A skipper caught out in the North Sea can run for a lee shore. A crew in trouble in the Gulf of Alaska can put a peninsula between themselves and the weather. In the Labrador Sea, the two shores that exist are the two shores you least want. The Labrador side is a low, fjord-cut, largely unlit coast that is guarded in winter by moving pack ice pressing south, which means the coast you would run toward is behind a barrier that closes and opens on its own schedule. The Greenland side is worse in a different way because the ice that arrives there is not flat pack, but hard glacial ice calved off the western glaciers, and the current that carries it runs directly along the coast you would be trying to reach. Running for shelter in this basin is often a decision to swap one hazard for a denser one. So the first thing the geography takes away is the option that every mariner is trained to reach for. There is no lee. There is no dogleg into a fjord that does not involve threading between ice and rock in the dark. If the weather turns while you are in the middle of that basin, the middle of that basin is where you stay. And every hour of the storm is an hour you have to survive in place rather than escape. Which raises the question that ran underneath everything that follows. This is cold water. The Labrador Current running south down the western side sits at or below zero for much of the year, cold enough that its surface freezes over shelf and shore each winter. Cold water is supposed to be calming. Cold water suppresses convection in the atmosphere, flattens out instability, kills thunderstorms. Fishermen in the tropics understand this instinctively, which is why hurricanes die when they cross into cooler seas. So why does one of the coldest open basins in the Northern Hemisphere routinely manufacture some of the most violent, fastest deepening low-pressure systems in the Atlantic? Because the water out in the deep center of that basin is not cold in the way people assume, and because the air that arrives above it is far colder than anything the water can match. Here is what is actually stacked in that basin. Coming up the Greenland side is the West Greenland Current, and inside it is a body of water that began its life far to the south and east, in the Erminger Sea. Erminger water is warm and salty by North Atlantic standards, and it curls around the tip of Greenland and pushes north, sliding under the fresher, colder surface layer that comes out of the Arctic. So the basin ends up layered, a thin, cold, relatively fresh lid on top, and beneath it, at roughly 200 to 700 meters, a reservoir of comparatively warm, salty Atlantic water. The surface may sit near zero. The layer under it is several degrees warmer and holds an enormous amount of heat. Now bring in the air. In winter, the interior of northern Canada builds one of the coldest air masses in the hemisphere, And when the pressure pattern lines up, that air is pushed offshore. It crosses Baffin Island and Labrador and comes out over open water at temperatures that can sit around minus 25 degrees Celsius. And it is bone dry because it has spent the previous week over frozen ground and snow. That air arrives over a sea surface that may be at +3. The temperature difference between the water and the air immediately above it can be nearly 30 degrees. Water gives up heat to air across that kind of gap with brutal efficiency. Oceanographers measure it as a heat flux in watts per square meter, and in the Labrador Sea during a strong cold air outbreak, the number runs past 400 watts per square meter over enormous areas, and in the worst events, pushes toward 1,000. Translate that. 1,000 watts per square meter is roughly the power of full overhead sunshine, except pointed the wrong way. The ocean radiating and evaporating its heat upward into the air, square meter after square meter, across an area the size of a country for days. You can see it happening. When that air moves over that water, the sea appears to smoke. Water evaporates off the surface, hits the freezing air a few centimeters above it, and condenses instantly into a dense white fog that streams off the wave tops and rises in columns. Mariners call it sea smoke or Arctic smoke, and crews who have worked those waters describe visibility dropping to almost nothing at deck level, while the sky overhead stays clear. It looks strange, and it looks beautiful, and it is the visible signature of the ocean, dumping its heat into the atmosphere at a rate that will, within hours, be used to build the thing that kills them. Because all that heat and moisture goes somewhere. It feeds directly into any low-pressure system that happens to be sitting over the basin, and it feeds it fast. A weak disturbance drifting off the Canadian coast can pass over that warm subsurface reservoir, tap the heat pouring off it, and deepen explosively. Pressure falling 24 millibars or more in 24 hours. The classic definition of a bomb cyclone. The storm does not arrive from somewhere else and cross the Labrador Sea. The storm is often assembled inside the Labrador Sea, out of the sea's own heat, above the ship it is going to hit. That distinction matters more than it sounds. A storm that travels toward you can be tracked, and tracking gives time. A storm that grows on top of you gives you the length of time it takes to grow, and in this basin, that can be less than a day. For centuries, this was the fundamental unfairness of the place. Not that the weather was bad, but that the weather was made locally, out of ingredients no one on deck could see, in a layer of water several hundred meters below the keel. Add Greenland to it, and the geometry gets worse. Greenland is not a coastline in the meteorological sense. It is a wall. An ice dome rising to over 3,000 meters, dense cold air pooling on top of it, air that cannot simply flow across. Approaching westerly winds are forced to go around, and the southern tip of the island, Cape Farewell, acts like the corner of a building in a gale. Air piles up on the upwind side, accelerates around the point, and spills down the slope on the far side, and the result is a narrow, savage jet of wind that meteorologists have studied for decades under the name of the Greenland tip jet. Doyle and Shapiro described the mechanism in 1999. Later work using satellite scatterometer data and reanalysis records, including studies by Kjetil, Robert Pickart, and colleagues, showed how often these events occur in winter and how hard they hit. Peak winds reaching and exceeding 30 meters per second, with heat fluxes under the jet running to several hundred watts per square meter, and the whole event frequently lasting less than a day. 30 meters per second is a little over 100 kilometers an hour, sustained, at sea level, in a corridor that can be under 100 kilometers wide. It is not the strongest wind ever recorded anywhere. What makes it dangerous is where it starts. It does not spin up somewhere out in the ocean and travel toward Cape Farewell. giving anyone downwind a day of warning. It is generated by the mountain itself, right at the corner, and a vessel rounding the tip of Greenland can be in ordinary gale conditions and then inside the jet within an hour or two, because the jet is the corner, and the jet does something else. All that violent wind, all that heat stripped off the surface, cools and densifies the top layer of the ocean. Cold, salty surface water is heavier than the water beneath it, and when it becomes heavy enough, it sinks. Not in a trickle, but in plumes. Straight down through the water column, hundreds of meters, and in the strongest winters far more than that. This is open ocean deep convection, and there are only a handful of places on the planet where it happens on a large scale. The Labrador Sea is one of them. The water that is on the surface being whipped into spray in February can be at 1,500 or 2,000 meters by March, on its way to becoming part of the deep circulation of the entire Atlantic. Remember that because it explains something that looks irrational later. Why, in the 20th century, people deliberately put ships and crews into the worst part of this basin in the worst month of the year, on purpose, and kept doing it. First, the immediate consequences on deck. When a storm builds locally over deep water, the wind starts pushing waves in a basin that offers hundreds of kilometers of clear fetch, and there is nothing to interrupt them until they reach a shelf. Then, they reach the Labrador shelf, and the physics change. Waves entering shallower water slow down and steepen. Their crests bunch closer together. A long, high, survivable swell in deep water can become a shorter, steeper, breaking sea in 200 meters of water. And the difference between those two sea states is the difference between a ship rising over a wave and a ship being hit by one. Then add the current. The Labrador current runs south along that shelf, and the storms that matter often push wind from the south or southeast straight into it. When wind and current oppose each other, the waves get compressed. The spacing between crests shortens, and the faces get steeper, for exactly the same wind and the same energy. A vessel meeting that sea does not get the recovery interval it was designed for. It takes an impact, and before the bow has finished coming up, the next crest arrives. Anyone who has been aboard a working boat in an opposing tide understands the sensation at a small scale. Scale it to a subpolar gale over a shelf edge, and the boat stops behaving like a boat and starts behaving like an object being struck repeatedly. And then, the piece that has killed more crews in these waters than any single wave. All of that steep-breaking, wind-driven water is being torn apart at the crests and thrown into the air, and the air is at -15. Spray leaves the sea near 0 degrees, cools in flight, and lands on steel that is already far below freezing. It does not run off. It freezes where it lands, on rails, on rigging, on antennas, on wheelhouse windows, on the anchor gear, on every horizontal and vertical surface forward of the bridge. The weight itself is not the main problem. The location of the weight is. Ice accumulates highest on the parts of a vessel most exposed to spray, which are the parts that stick up: masts, aerials, upper works, deck cargo. Every ton that freezes onto rigging is a ton added far above the waterline, and a vessel's stability depends on keeping its center of gravity low. As ice builds up top, the center of gravity rises. The vessel rolls more slowly and returns to upright more sluggishly. Its righting ability, the force that brings it back from a heel, shrinks. In severe icing events, that reserve can be consumed in hours. Crews know this, and they fight it in the most primitive way available. They go out on deck in the middle of the storm with axes, baseball bats, mallets, and steam hoses, and they chip. It is exhausting. It is done at night in freezing spray on a surface that is itself sheeted in ice. And it is dangerous enough that men have been lost overboard doing it. Guidance issued to mariners in Canadian and American waters is blunt about the arithmetic. Under severe icing conditions, manual removal may be the only thing preventing a capsize. And the decision that actually matters is whether the ice is accumulating faster than the crew can remove it, and how long the storm is forecast to last. If the answer is that it is winning, the vessel has to change what it is doing. Turn, slow, alter heading to reduce spray, run for shelter, and every one of those choices costs something else. That is the machine. Cold continental air crosses warm subsurface water. The ocean gives up its heat. A storm builds in place. The mountain at Cape Farewell accelerates the wind. The shelf and the opposing current steepen the sea, and the sea then delivers itself onto the ship as ice, above the center of gravity, where it does the most harm. Every part of that chain has been measured. None of it is mysterious, and it has been running, unchanged in its essentials, for as long as anyone has been putting boats into this water, which is the part that should bother you. Because the first Europeans who worked this coast in an organized, industrial, profit-driven way did not have engines, radios, forecasts, radar, or steel. They came in wooden sailing ships with no way to go upwind properly, no way to call for help, and no possibility of rescue. By any reasonable measure, they should have been slaughtered. They mostly were not. And the reason they were not is the single most useful idea in this entire story. In the middle of the 16th century, ships began arriving on the southern Labrador coast from the Basque Country, from ports like Pasaya, San Sebastian, Bermeo, Guiteria, Zarautz. And they came for one product: whale oil. Rendered blubber, boiled down in stone furnaces on the shore, and poured into oak casks, sold in Bristol and Antwerp and Seville to burn in lamps, to make soap, to treat wool and leather. It was one of the most valuable bulk commodities in Europe, and the Strait of Belle Isle, the narrow channel between Labrador and the northern tip of Newfoundland at the southern gate of the Labrador Sea, was where the whales funneled through. The scale of what happened there was hidden for 400 years, and it was recovered almost single-handedly by one person. Selma Barkham was a Canadian historical geographer who moved to Spain in the early 1970s and spent years working through provincial archives, Oñati, Burgos, Valladolid, the notarial records of small Basque towns. What she found were not chronicles or adventure narratives. They were the paperwork of an industry: marine insurance policies, shipbuilding contracts, crew agreements, provisioning lists, lawsuits over cargo, and wills. Documents that had sat unread for centuries because nobody had thought to ask whether ordinary Basque commercial records had anything to say about Canada. Out of them, Barkham reconstructed a functioning transatlantic whaling economy, and she was able to name the places on the Labrador coast where it operated. Then she did something that historians rarely get to do. She told archaeologists where to dig. In 1978, working from her research, a Parks Canada team went to Red Bay, on the Labrador shore of the strait, and found a 16th-century Basque whaling galleon on the harbor floor. It is generally identified as the San Juan, lost there in 1565. Over several seasons, the site produced one of the most complete pictures of a 16th-century working ship anywhere in the world. Hull timbers, barrel staves by the thousand, and a chalupa, the small open whaleboat the men actually rowed at whales, preserved beneath the ship. On Saddle Island at the harbor mouth, archaeologists located the try-works, where the blubber was rendered, the cooperage where the casks were made, and in 1982, on the eastern end of the island, a cemetery. That cemetery is the part that should stay with you. 4 summers of excavation revealed more than 60 graves containing the remains of more than 140 individuals. Nearly all were adult males in their early 20s to early 40s. 2 were 12 years old. Estimates for the site as a whole run to roughly 150 burials across a whaling enterprise of some 50 years, which works out to an average of around 3 men a year who did not go home. 3 a year. Out of a seasonal population that ran into the high hundreds at Red Bay alone, and something on the order of a couple of thousand men across the Labrador stations in a good year, working in open boats at the edge of the Labrador Sea with hand harpoons, against animals larger than their vessels, 400 years before antibiotics, with no rescue of any kind available. That is a survival rate that would embarrass a great many better-equipped expeditions that came later. They achieved it with a calendar. The Basque season was governed by ice, and everybody in the industry knew the dates. Ships crossed the Atlantic in late spring and early summer, arriving in June or July. They fished through the summer and into the autumn, which was when the whales were best and the oil yield highest, and then they left. The whole operation was structured around being off the coast and headed east before the ice arrived, the pack pushing south along the Labrador shore and the fast ice forming in the bays and harbors themselves. Provisioning lists, crew contracts, and insurance terms were all built around that window. It was not folklore. It was commercial practice, written into paper that survives. And the reason it was written into paper is that everyone involved understood what happened to a ship that missed the window. They understood it because it happened. In the seasons of 1574 to 1575, and again in 1576 to 1577, Basque ships stayed too long on the Labrador coast and were caught. The documentary record is clear that the results were disastrous for the crews. The mechanics are not hard to reconstruct. A ship that is still loading in late November is a ship whose captain is looking at a hold that is not full, and a crew paid in shares of the cargo. Another few whales is another few hundred ducats, and the harbor is still open. You can see it. It is right there. The water is moving. Ice does not close a Labrador harbor gradually and politely. Fast ice forms in the shelter first, at the head of the bay, precisely where a ship rides at anchor, and the pack arriving from the north can shut the seaward approach in a matter of days, when the wind sets right. The route out closes before the water looks closed. Then the arithmetic becomes very simple and very bad. A wooden ship frozen into a Labrador harbor is not a shelter. It is an unheated hull, and the crew moves ashore into whatever the station provides. Turf and timber structures built for a summer working season, not a subarctic winter. Provisions were loaded for a voyage and a season, not for 8 extra months. There is no fresh food after the last of the autumn birds and fish. Scurvy arrives in weeks, and scurvy in the 16th century was untreatable by anything these men had. The nearest other Europeans were at another station along the same closed coast. The nearest help of any kind was across the Atlantic and would not be thinking about them until June. We have a document from inside that world. On Christmas Eve in 1584, at a Basque station on the Labrador coast, a dying whaler named Joannes de Echeniz had his will written down. It is the first known will made in what is now Canada, and it survives because it went back into the notarial system in Spain, where Barkham eventually read it. It is not a dramatic text. It is a man in a cold place, disposing of what he owned, making sure his family got it. And it exists because he was somewhere he was not supposed to be at that time of year. So here is what the Basques prove, and it should be said bluntly. Their safety system was not equipment. Their ships were slow. They could not work to windward. They had no charts worth the name, no instruments beyond a compass and a lead line, and absolutely no possibility of assistance. What they had instead was a rule about time, and the discipline to obey it in the face of money telling them not to. And even the discipline did not always save the ship, which brings us back to the wreck on the bottom of Red Bay Harbor. The San Juan was doing everything right. She was in harbor. The good harbor, the sheltered one behind Saddle Island, chosen precisely because it gave protection from the strait. She was loaded or close to it, roughly 1,000 barrels of oil according to the archival picture, which represented a full season of work by dozens of men and an investment that would have been insured financed, and argued about by merchants 3,000 miles away. She was by any measure at the safest moment of the entire enterprise. Cargo aboard, crew alive, homeward voyage next. Then a storm came through the strait, and she sank at her anchorage. Think about the sequence there, because it recurs in this basin for the next 4 centuries. The vessel had already made every correct decision. She had reached shelter. Shelter is what mariners are trained to reach. And in the Labrador Sea, shelter along a low rock-fringed coast that faces an open strait means a shallow anchorage with limited swinging room and a bottom that gives poor holding, entered because the alternative was worse. An anchored ship in a shallow harbor during a gale has almost no options. She cannot run, she cannot maneuver, she can veer more cable and hope, and if she drags, she has a few hundred meters of water before the rocks. A ship at sea can at least be handled. A ship at anchor has already spent that choice. The crew survived. There is no record of the San Juan's loss being a mass casualty event, and the salvage effort afterwards recovered a substantial part of the oil, which is exactly what a crew with a wrecked ship and a valuable cargo in shallow water would spend the remaining weeks doing. They would have worked from boats over the sunken hull, in October water, hauling casks. Then they went home in other ships because there was a fleet on that coast, and berths could be found. So the outcome was, the ship is gone, the cargo is mostly recovered, the men are alive. That is not a catastrophe. That is a bad year. And it is the first appearance in this story of a pattern that will get much stranger later. The vessel is expendable, and the people are not. And the difference between those two outcomes is usually a question of how close the disaster happened to somewhere people could stand, which points at the real limit of the Basque system. Their entire survival model depended on being able to physically remove themselves from the region before conditions changed. It worked because their operating season and the dangerous season did not overlap. They were not managing risk in the Labrador Sea in winter. They were absent from the Labrador Sea in winter. That is a completely different thing, and it only works as long as nothing gives you the ability to be there in January. Sail gave them no such ability. So the rule held. The rule held for the French and English crews who followed them into the strait, and for the Newfoundland schooners after that. A vessel that depends on wind cannot reliably beat out of a closing bay against a northerly, cannot hold position off a lee shore in a gale, and cannot make a passage on a schedule. If you cannot guarantee arrival, you plan around the season. The season becomes the safety margin, whether you like it or not. Take that away. Give a captain an engine that will drive the ship into a headwind at 8 knots, and a hull sheathed to push through young ice, and a chart, and eventually a radio, and something quietly poisonous happens. The reason for the rule disappears from view before the danger does. Winter stops being a wall and starts being a difficulty, and difficulties are things a commercial operation negotiates. The season stops setting the schedule, and the schedule starts arguing with the season. That shift took about 350 years to complete, and when it did complete, it produced the loss of the Hans Hedtoft. But before the engines arrived, there was a group of people on this coast who had a far more sophisticated version of the Basque calendar, who used it year-round rather than seasonally, and whose approach to the ice was not avoidance at all. Inuit had been living along the Labrador coast and around the northern rim of this basin for centuries before a Basque cask was ever filled, and their relationship with the winter ice was the exact opposite of avoidance. For them, the ice was not the thing that closed the coast. It was the thing that opened it. Sea ice is a road. It is the only surface that lets you travel long distances along a fjord-shredded coastline in the dark half of the year, and it puts you within reach of seals, which is to say within reach of food, fuel, and clothing. Using it requires knowing it, and the knowledge is far more granular than outsiders tend to assume. In Nain, the northernmost community on the Labrador coast, A group of elders and knowledge holders formed a committee called Sikushu Tet, people who live on the ice, and spent 2 years assembling a reference of sea ice terminology in Inuktitut and English. Published through the community organization Smart Ice in 2023, it contains 51 distinct terms with photographs, 51 named categories for a substance most people would describe with one word. None of that is decoration. Every term is an operating instruction. There is a word for the ice that is frozen fast to the land and holds your weight and your chromatic. There is a word for the moving pack beyond it. And there is a word for the line where the two meet, the Sena, the ice edge, which is simultaneously the best hunting ground on the coast and the single most lethal feature in the entire system. The Sena is dangerous because it is not a line. It is a negotiation between the shore-fast ice and the ice that is drifting south on the current, and it moves. It establishes itself as winter sets in, and it advances and retreats with wind, tide, current, and temperature. Stand on the wrong side of it, with an offshore wind behind you, and the pan you are standing on can detach and start moving out into the Labrador Sea. And there is nothing on that pan that will get you back. The knowledge that keeps a hunter alive there is not a rule, but a running assessment. Color, thickness, the sound the ice makes, the way snow has drifted across it, where the tide cracks run, what the current did last week, which way the wind has been for the last 2 days, and whether it is doing something new today. Here is the crucial difference, and it is the idea the rest of this story keeps testing. The Basque system was a schedule. Be gone by December. It worked, but it was rigid, and it only worked as long as nobody had a reason to break it. The Inuit system was continuous observation with the authority to stop. Nobody was going out on the ice on Tuesday because it had been planned for Tuesday. They went when the ice said they could go, and the decision was made fresh every time, by the person who would pay for getting it wrong. Turning back was not a failure in that system. It was the system. Compare that with what arrived. In 1771, 14 Moravian brethren led by Jens Haven landed on the North Labrador coast and founded 9, the first permanent mission to Inuit in what became Canada. Okak followed, then Hopedale, then Hebron in the 1830s, strung up a coast that in winter is entirely unreachable by sea. The Moravians were not casual visitors. They were there for the long term, they learned the language, they kept meticulous records, and those diaries and letters are among the best continuous written observations of Labrador weather and ice conditions that exist for that era. And they solved the transport problem in a way that is quietly revealing. The mission was supplied by a series of ships out of London, 12 vessels over the life of the operation, 5 of them named Harmony. And they made one voyage a year. One. North in the summer, deliver a year of provisions, rotate personnel, take the year's produce and correspondence back, and be out before the coast closed. That single annual sailing continued for 156 years, from 1770 to 1926. 156 years, and the schedule barely changed, because the schedule was not really theirs. The coast set it. An organization with money, ships, a global network, and every incentive to be efficient, looked at the Labrador Sea and concluded that the correct number of winter crossings was 0, and then held that position for over a century and a half. Whatever else the Moravians got right or wrong on that coast. And their record with Inuit communities is a genuinely complicated one, including the closure of Hebron in 1959 and the forced relocation of the families who lived there, a decision that people in Nunatsiavut are still living with. On the specific question of when to be at sea in this basin, the institution deferred completely to the environment. So by the middle of the 19th century, you have 2 coexisting models on the same coast. One is indigenous, continuous, observational, and treats the ice as terrain to be read. The other is European, institutional, schedule-based, and treats the ice as a period of closure to be waited out. They disagree about almost everything except the one thing that matters. Neither of them is out in the middle of the Labrador Sea in February. Both are about to be overruled, and not by a change in the weather. What changed was steel, coal, and eventually diesel. A powered vessel does not care which way the wind is blowing. It can hold a course, hold a position, punch out of a bay against a northerly. And this is the part that matters. It can be scheduled. It can be promised to arrive on a date. Once a vessel can be promised, it starts being sold, insured, contracted, and timetabled, and the people making those promises are on shore. Then, the vessel gets reinforced. Ice-strengthened hulls, thicker plating at the bow and along the waterline, frames closer together, propellers and rudders protected. A ship built like that can shoulder through young ice that would have stopped a wooden schooner cold. And every one of those improvements is real. This is not a story about technology being fake. The ships genuinely were stronger, the engines genuinely did work, and thousands of voyages were made safely that could not have been made at all a century earlier. The problem is what the improvement gets spent on. An engineer designs a stronger hull to increase the margin of safety on the voyages people are already making. An operator looks at the same hull and sees a vessel that can make voyages nobody was previously making. The extra capability does not sit in the account as unused safety. It gets converted into new routes, later departures, earlier arrivals, a longer season, one more trip before the ice. The margin is not banked. It is spent, and none of it reaches the machine underneath. Reinforcement is a defense against contact. Power is a defense against wind. Neither is a defense against a low deepening over your head faster than you can get anywhere, and neither shortens the distance to the nearest port by a single mile. Technology changed what people could attempt in this basin. It changed remarkably little about what the basin would do to them once they were out in it. There is a way to watch that gap open in real time, and it involves a fishery that ran for centuries, employed tens of thousands of men, and killed them in a manner that had nothing to do with storms, ice, or any of the forces described so far. It killed them with fog. The same Labrador current that freezes spray onto a wheelhouse in February does something else entirely in July. It sits there at or barely above zero, along the shelf and out over the banks. And in summer, the air moving in from the south and east over the warmer Atlantic is mild and saturated with moisture. When that air slides over the cold current, it is chilled from below, and the water it is carrying condenses. The result is advection fog, and it forms in sheets that can cover tens of thousands of square kilometers and sit for days. The waters off Newfoundland and Labrador are among the foggiest on the planet, and it is the same current doing it. The cold making smoke out of warm air in summer, and making ice out of cold air in winter. Into that fog, for something close to 470 years, Portugal sent men in rowing boats. The Portuguese cod fishery on the banks off Newfoundland, Labrador, and West Greenland ran from the early 16th century to 1974. In its final century, it was conducted by big sailing schooners, later motor trawlers, but the schooners are the point, and the method was as follows. The mothership anchored or drifted on the fishing ground. Stacked on her deck were dories, small, flat-bottomed open boats, 4 or 5 meters long, built to nest inside each other. Each morning the dories were put over the side and each one took a single man. One man, alone. With oars, a compass, bait, hand lines or long lines, a bailer, and food for the day, he rowed away from the schooner until he was on fish. And he stayed until his dory was loaded with cod, which meant staying until the boat was low in the water and dangerous, because a light dory meant a bad day, and pay was tied to what you brought back. Alan Villiers went and did it with them. Villiers was an Australian-born sailor and writer with a hard-earned reputation for actually going to sea rather than writing about it from shore. And in 1950 he shipped out on the four-masted Portuguese schooner Argus for a 6-month campaign. The Grand Banks first, then north along the west coast of Greenland. What he published the following year, The Quest of the Schooner Argus, is the closest thing we have to a first-hand technical record of that fishery in its last decades. And it is not a romantic book. It is the account of a man watching other men work themselves to the edge of what a human body will do, in an environment with no forgiveness in it at all. The fog is the recurring problem in every account of that fishery. And to understand why, you have to think about what a doryman's navigation actually consists of. He is in a boat with no engine, sitting perhaps 60 centimeters above the water. His visual horizon on a clear day is a few kilometers. He is working 3, 5, sometimes more kilometers from the schooner. He finds his way back by compass, bearing, and by sound. The schooner's bell, her horn, and in later years, a siren. He carries a horn of his own. In the Portuguese fleet, a conch shell was the traditional instrument, and men blew them to raise the ship or to warn other dories. Then the fog comes in, and every one of those systems degrades at once. Visibility goes to a few boat lengths. That alone is survivable, because he has a compass. The compass, though, gives him a direction, not a position. And the schooner is not where he left her. She has been drifting on wind and current all day, and so has he. And the current here runs at a real speed. So the bearing he took in the morning now points at a patch of empty water. He corrects by ear, and that is where the environment does something genuinely cruel. Fog does not simply muffle sound. Fog forms in a temperature inversion. Cold air below, warmer air above. And sound traveling through an inversion is bent upward, away from the surface. A horn sounding 2 kilometers away can be perfectly audible at 4 kilometers and completely inaudible at 1, because the sound has been refracted over the top of the listener. Mariners have documented these silent zones for well over a century, and lighthouse services studied them precisely because fog signals were failing in exactly the conditions they were built for. It also plays with direction. Sound arriving through layered air and reflecting off the water surface can seem to come from the wrong quarter. A man rowing toward a horn he can hear clearly can be rowing away from the ship. So the doryman rows. He has a boat full of fish, which makes it heavy and slow and low. And the sensible thing would be to dump the catch to lighten it, which is also the thing that costs him his day's earnings and, in the Portuguese system, part of his season. He has water sometimes, and biscuit sometimes. He has no radio. Nobody knows exactly where he is, including him. Some of them were picked up hours later. Some were picked up days later by another vessel. Some were never found. The Portuguese fleet lost men this way steadily year after year, and while the totals across the whole history of the fishery are not precisely recoverable, the consequences are physically visible. There are Portuguese fishermen buried in Newfoundland, in graves that fleet veterans and their descendants have returned to find and mark in recent decades. That is what the loss rate looks like at ground level, not a disaster with a date on it. A slow, distributed, accepted attrition. And here's the part that connects it to everything else in this basin. Nothing dramatic had to happen. There was no storm in that scenario, no ice, no wave, no mechanical failure. Conditions were flat calm. The temperature was above freezing. What removed the man's options was a change in visibility, and visibility is not a force. It does not break anything. It just deletes the information you were using to stay alive. And this coast manufactures that deletion on an industrial scale out of the same cold current that does everything else here. Why did they keep doing it? Because the fishery was not a personal choice. In 1934, the Salazar government in Portugal restructured the cod industry around what became known as the Codfish Campaign, centralizing it under state-backed guilds and cartels that controlled quotas, licensing, crewing, and prices. Salt cod was a strategic food supply and a matter of national policy, and the fleet sailed under an arrangement in which the state, Cirque Dauphine Chimkraon Messenger, the Shipowners Guild, and the crews were all locked into the season. During the Second World War, the hulls were painted white to mark Portuguese neutrality, which is where the name that stuck, the White Fleet, came from. A doryman who decided the fog was too thick was not making a private risk assessment. He was making a decision about a system that had already committed him. That system knew what it was doing to its men, and it responded in a way that tells you a great deal about how far from help these grounds were. It sent a hospital. From 1927, Portugal dispatched a dedicated support ship to accompany the fleet across the Atlantic. And in 1955, the shipyards at Viana do Castelo delivered a purpose-built replacement, the Gil Eans. She served as the flagship of the White Fleet from 1955 until 1973, and her job list is a summary of everything the Labrador and Newfoundland grounds denied to the men working them. She was a hospital ship with an operating theater and treatment rooms. She was the mail ship. She was the maritime authority. She was a tug. She had ice capability. She carried supplies, fresh water, and bait, and she moved between the vessels of the fleet across an enormous stretch of the North Atlantic. Think about what has to be true for that to make economic sense. You build and crew a full hospital vessel and send her across an ocean for months because the alternative, a man with a crushed hand or appendicitis or hypothermia being landed at a port, costs you the vessel's entire fishing time. St. John's is days away from the northern grounds under sail. Greenland is further. Portugal is 3,000 miles away. So the medicine has to come to the fleet, because the fleet cannot go to the medicine. Pin that down, because it is the first honest statement of the rescue problem in this story, and it is the constraint that never improves. Distance is not a technology problem. It is a geometry problem. You can put a surgeon in the middle of the Labrador Sea, and the Portuguese did. What you cannot do is put him next to the specific dory that has gone missing in fog 40 kilometers away in time. The Gil Eans is still afloat, preserved at Viana do Castelo as a museum ship, and you can walk through the operating theater. It is small, and the equipment in it is of its period, and it is the most eloquent object in this entire history. A country's admission, in steel, that it had sent its people somewhere help could not reach. The last White Fleet vessel sailed from St. John's in 1974. By then, the industry had moved to steel trawlers with radar, radio, and echo sounders, and the dory era ended. And with it, that particular way of dying. The fog did not go anywhere. It is still there every summer, forming out of the same current for the same reason. What changed was that the men were no longer sitting in it in open boats, so each of these systems worked within its limits. The Basques used a calendar. Inuit used continuous observation. The Moravians used one sailing a year. The Portuguese used a hospital ship and accepted the losses. Every one of them was an admission that this basin would not be negotiated with directly. Then came a generation that decided it did not have to touch the water at all. In 1942, the United States had to move thousands of aircraft to Britain, and the obvious method, putting them on ships, was being defeated by U-boats and by simple arithmetic. Deck space was scarce, crated aircraft had to be reassembled, and every fighter on a freighter was a fighter that might go to the bottom with it. The alternative was to fly them across. Bombers could just about do it. Fighters could not. A P-38 Lightning had the legs for a long leg, not an ocean, so the aircraft were routed across the top, in hops, using the only land available. Presque Isle in Maine, then northeast to Goose Bay in Labrador, a base carved out of the interior in 1941 specifically because there was nothing else there. Then across the Labrador Sea to Greenland, to airfields, the Americans had built and given code names. Bluey West 1 at Narsarsuaq near the southern tip, and Bluey West 8 further up the west coast at Söndre Strömfjord, from Greenland to Reykjavik and from Iceland to Scotland. The buildup this served was Operation Bolero, and the ferry route was its artery. Look at that chain of stepping stones on a map and notice what it does. It takes an aircraft with limited endurance and flies it repeatedly, directly across the Labrador Sea and around the southern end of Greenland, over the exact water where storms assemble themselves out of the ocean's own heat, and past the exact corner where the ice dome bends westerly wind into a jet. The route was not designed to be safe. It was designed to be possible. And it inherited a specific structural disadvantage. Weather in the North Atlantic moves broadly west to east. An aircraft flying east from Labrador to Greenland is flying downstream into weather that forms ahead of it, over water where in 1942 there were very few observers of any kind, a handful of ships, a few stations, no satellites, no radar coverage over the ocean, no reliable picture of what was building out there. Forecasters could tell you what the air had been doing over Canada. They could not tell you with confidence what it was doing at that moment 2 hours ahead over the middle of the basin. Which is how, on the 15th of July, 1942, 6 P-38 fighters and 2 B-17 bombers with 25 men aboard came to be over Greenland with nowhere to go. They had launched to continue east. The objective was routine, another leg of a ferry flight, in summer, in daylight that in those latitudes barely ends. The formation flew with the bombers navigating and the fighters keeping station, which is how it was done. The single-seat aircraft had no navigator, so they tucked in behind aircraft that did. That arrangement worked as long as the formation stayed together, and the destination stayed open. The weather ahead deteriorated. Cloud, poor visibility, conditions that would not let a formation of 8 aircraft continue toward a destination it had to find visually. The decision to turn back was correct and unremarkable. Aircraft turn back constantly. This is what fuel reserves exist for. The problem is, the reserve is a one-way instrument. The moment they reversed course, every kilometer they had flown east had to be flown again west, out of the same tanks. And now they were burning through the margin that had been set aside for exactly this situation. Fighters carry less of it than bombers, and the field they were heading back toward was in Greenland, where the approaches are not forgiving. Bluey West 1 sits at the head of a fjord, and getting into it means flying up a valley with mountains on both sides and no room to turn around. In cloud, that approach is not an option. It is a way of hitting rock. So the aircraft that had turned back because of weather were now looking for a field whose usability depended on the same weather. They could not get in. The accounts differ in some details of what each pilot saw and when, but the operational outcome is not in dispute. 8 aircraft running down their fuel in cloud, unable to reach a usable runway over Greenland. What was under them was the ice cap. It is the largest landmass feature in the North Atlantic, and it is, from a pilot's perspective, an enormous white surface that is broadly flat, extremely hard, and completely without visual reference. Judging height above it in flat light is close to impossible because there is nothing to judge against. It is also not uniformly solid. The edges are crevassed, and a crevasse under a thin snow bridge is invisible from any altitude. They put all 8 down on it. By the accounts that came out of the flight, the first aircraft to land tried it with the wheels down, dug into the surface, and flipped over. The pilot got out. Everyone who came after him landed on the belly, which is the correct technique and which also permanently ends the aircraft's flying career. One after another, 6 fighters and 2 4-engine bombers slid to a stop on the Greenland ice cap, and 25 men climbed out into the middle of it. Nobody was killed. Not on the landings, not afterwards. Every single man on that mission came home. They survived because of a set of conditions that will not repeat later, and those conditions deserve to be named precisely. It was July. The temperature was survivable with the clothing and gear they had. The daylight was effectively continuous, which meant search aircraft could look for them around the clock, and the men on the ice could be seen. They were on a solid surface rather than in water, and a solid surface is the single most important variable in cold region survival, because it removes the immediate heat loss problem and it gives rescuers somewhere to arrive. They were together, in a group, with 8 aircrafts worth of equipment, radios, parachutes for shelter, and rations. They were found relatively quickly, resupplied from the air, and then reached on the ground and brought out, a march off the ice and down to the coast with the assistance of dog teams, which in that terrain remained the most reliable transport available. They spent something on the order of a week to 10 days on the ice cap. Then they were gone, and the aircraft were not. Consider that decision because in wartime, it is a serious one. 8 combat aircraft, 2 heavy bombers, and 6 of the newest and most capable fighters the U.S. Army Air Forces had were written off, intact, on the ground, because there was no way to recover them. They were not shot down. They were not damaged beyond repair. They were simply somewhere that the most industrially powerful nation on Earth, at the height of a total war, could not retrieve them from. That is the environment making an economic argument, and the environment won it in about 10 days. Here is the reversal that matters. And it is the opposite of what you would expect from a story about a place this dangerous. The entire squadron was destroyed, and every human being walked away, not one casualty. The machines were expendable, and the people were not, exactly as with the San Juan at anchor in Red Bay 400 years earlier, and for the same underlying reason. The disaster happened somewhere people could stand, change the surface and the season, and that ratio inverts violently. Put the same men in the water instead of on ice and they have minutes. Put them on the ice cap in November instead of July, and the daylight vanishes. The temperature drops far below anything their equipment was built for, and the aircraft that would look for them cannot see them for most of the day. Which is precisely what happened 4 months later on the same ice cap, in the same theater to people trying to help. Before that, though, finish the story of the 8 aircraft, because it contains a fact about this region that is easy to miss. 50 years later, a group of aviation enthusiasts went back to get one. Finding the site was the first problem, and it turned out to be much harder than expected because the aircraft were no longer where they had been left. The Greenland ice cap flows. It is not a parking lot, it is a very slow river of ice. And over 5 decades, the aircraft had traveled well over a kilometer from the coordinates in the 1942 records. The second problem was depth. When the Greenland Expedition Society finally located and reached one of the P-38s, it was under 268 feet of ice and compacted snow. 82 meters. That is roughly the height of a 25-story building, accumulated on top of an aircraft in 50 years, at a site that had also moved sideways. They melted a shaft down to it, disassembled it underground, brought it up in pieces, and rebuilt it. The aircraft, now known as Glacier Girl, flew again in October 2002. Weigh those numbers for a second because they are the clearest available statement of what this corner of the world does to human traces. 25 men were on the surface of that ice cap for about a week, and it took every resource available to get them off. The metal they left behind was 82 meters down and a kilometer away within a single human lifetime. Nothing about that environment is passive. It is actively burying and transporting anything left on it continuously, and it does this to aircraft and to people with equal indifference. There is a coda that the Glacier Girl story tends to skip. In 2007, restored and airworthy, the aircraft attempted to complete the crossing it had failed to make in 1942, New Jersey to England by the northern route. It got as far as Labrador and had to stop with engine problems. 65 years, and the geography still had a vote. The reason the ferry route mattered so much in the winter of 1942, and the reason aircraft kept being pushed across it in worsening conditions, is that the war did not have a season. And that is where the second Greenland story begins. The one where the people who died were not the ones who crashed. On the 5th of November 1942, an Army C-53 Skytrooper with 5 men aboard went down on the Greenland ice cap. There was some radio contact at first, then there was not. Those 5 men were never found, and they are not the subject of what follows. They are the reason for it. Because when an aircraft goes missing in that country, other aircraft go looking. And on the 9th of November, a B-17F radio call sign PN-19E with 9 men aboard was flying a search leg for the C-53 when it flew into the ice. It is worth understanding how that happens to a competent crew in a serviceable aircraft. Over the ice cap in poor light, the surface and the sky can become the same color, and the horizon simply stops existing. There is no shadow, no texture, no contrast, nothing to fix the eye on. A pilot in a whiteout has no reliable sense of how high he is or whether he is level, and the instruments of 1942 give altitude above sea level, not above a sloping ice surface whose height he does not know precisely. Aircraft in those conditions do not dive into the ground. They fly into it while apparently in level flight, at cruising speed, still under control. PN-9E broke apart on impact. Every one of the 9 men aboard survived it. 9 men in a bomber that hit a glacier at cruising speed, and all 9 walked away from it. Keep that in front of you. It is going to be the whole point. They were now on the ice cap in November. Everything that had protected the 25 men of the ferry flight 4 months earlier was gone. The daylight was collapsing toward the polar night, which cut the hours in which anything could search for them, and made the hours it did have marginal. The temperature was no longer a nuisance, but a continuous injury. The surface underneath them, which in July had been the thing that saved lives, was now revealed as something else. This part of the ice cap was crevassed, and the crevasses were bridged over with snow, which meant the ground itself was a lie. It looked like a floor. In places, it was a lid. They found shelter in the broken tail section, established radio contact, and were located. Which is the good news, and worth pausing on, because from this point onward, everyone always knows exactly where they are. The information problem is solved on day 1. Their position is known, their condition is known. Aircraft can find them and drop supplies to them, and none of that gets them off the ice. That gap between being found and being reached is the thing this whole story keeps circling, and here is where it becomes explicit. Off the east coast of Greenland was the U.S. Coast Guard cutter Northland, part of the Greenland Patrol, and aboard her was a Grumman J-2F Duck, a single-engine amphibious biplane, big, slow, tough, with a boat hull under it and floats on the wings. Her pilot was Lieutenant John A. Pritchard, Jr., with radioman First Class Benjamin A. Bottoms. On the 28th of November, Pritchard flew inland and landed the Duck on the ice cap. That had not been done before. It was an amphibian, designed for water and runways, being deliberately put down on an unprepared, crevassed glacier surface, with no idea what was under the snow. He could not land at the wreck itself, so he set down some distance from it, and then he and Bottoms went the rest of the way on foot, across the same ground that had swallowed the aircraft, reached the B-17, and brought 2 of the injured men back to the Duck. He told the crew what the aircraft could carry. 2 more people. He would come back for the rest. Then he flew them out to the Northland, which meant taking off from an ice cap in an aircraft not built for it and finding a moving ship on a winter coast. And he did it. On the 29th, he went back. He landed again, took aboard 1 man, Corporal Lauren Howarth, the B-17's radio man, and lifted off. Within minutes, the weather closed. Bottoms was working the radio, and the Northland was tracking them by his transmissions. The signals grew weaker. At one point, the Duck's crew asked for a bearing back to the ship. Then, the transmission stopped. They had flown into whiteout. In an aircraft with no way to see over a surface indistinguishable from the air above it. When the wreckage was eventually spotted from the air, it was reported as badly broken, with no sign of life. Pritchard, Bottoms, and Howarth all died. Their remains have never been recovered. The wreck itself was located and then lost again, as the ice moved over and around it, and modern searches, including work by U.S. agencies and private recovery teams that has continued in recent years, at one point locating an aircraft under roughly 38 feet of ice, have not brought them home. Pritchard and Bottoms were posthumously awarded the Distinguished Flying Cross. 9 minutes. That is the interval, by the Coast Guard's own account, between Howarth being lifted off the ice and the aircraft going in. Now count what the environment has taken so far. The crash of PN-9E. 0 deaths. The attempt to reach the survivors. 3. And it was not finished. While the air rescue was being attempted, an overland approach was also underway, because in that terrain, a ground party is not an absurd idea. It is often the only idea. Lieutenant Max Demarest was a glaciologist, a man whose profession was the behavior of ice, working with motor sleds to reach the site across the surface. He had already been involved in getting men out. On the same day the Duck was lost, Demarest drove his sled into a deep crevasse and was killed. Read that again. The person on the entire operation with the most specialized knowledge of exactly this hazard was killed by exactly this hazard, not through carelessness, because a snow bridge over a crevasse is invisible, and the only way to find out whether the surface will hold is to put weight on it. Then the ice took one of the survivors the same way. Sergeant Clarence Weddell, moving on the surface during a rescue attempt, broke through a shallow bridge over a deep crevasse and was gone. 5 dead. Lauren Howarth and Clarence Weddell from the aircraft, and John Pritchard, Benjamin Bottoms, and Max Demarest, who came to help. Every single one of them died after the crash during the effort to undo it. The remaining men stayed on the ice cap. Not for days, for months. The mathematics of the situation were now brutally clear to everyone involved. Aircraft could find them and could drop supplies, and did. Food, fuel, clothing, radio batteries. What no aircraft could reliably do was land near them and take off again. Every attempt to reach them by air or by surface had cost lives, so the operation shifted from rescue to sustainment. Keep them alive, and wait for the light and the weather to change. They lived in the wreckage and in shelters dug into the snow. They rationed. They dealt with frostbite with what they had, which was not much, and injuries that would have been minor at a base became slow catastrophes. They listened for aircraft. Men in that position develop an intense relationship with engine noise, because the sound of an approaching aircraft is the only event in a landscape where nothing else happens. The solution, when it came, was proposed by a man who had spent his career refusing to accept polar geography as final. Lieutenant Colonel Bernt Balchen was a Norwegian-American aviator with more cold region flying experience than almost anyone alive. He had flown in Antarctica with Byrd. Balchen's idea was to take a PBY Catalina, a large twin-engine flying boat, an aircraft designed to land on water, and deliberately belly-landed on the ice cap. It is a genuinely strange piece of engineering thinking, and it worked because of one specific property. A flying boat has a hull. Its underside is built to take the impact and friction of landing on a surface, and snow, if you pick your spot, behaves enough like water to let a hull slide. Balchen and Lieutenant Bernard Dunlop put a PBY-5A down on the ice cap 3 times between February and April 1943, taking men off in batches. On at least one of those landings, the aircraft stuck in the snow and would not accelerate. and the men aboard climbed out onto the wings and jumped up and down on them to rock it loose before it would move enough to fly. That is how the rescue of a United States Army bomber crew was accomplished in 1943, by bouncing on the wings of a seaplane parked on a glacier. The Coast Guard's own account of the affair records it running from the 5th of November 1942 to the 18th of May 1943, well over 6 months from the first loss to the last man out, in a theater a few hundred kilometers across, in a war the United States was fighting on 2 oceans with the largest industrial base on the planet behind it. So here is what this proves: that the ferry flight did not. The July Squadron established that this environment will destroy machinery and let people walk away, provided the season is right and the surface is solid. The winter of 1942 to 1943 established the price of the same accident with the season changed, and it established it in a very specific way. The danger was not concentrated in the crash, it was concentrated in the response. Everyone who died during the rescue, and 3 of them died because they voluntarily entered the same conditions that had brought down the aircraft they were trying to reach. That is not bad luck. It is structural. A rescuer going to the scene of an environmental accident is, by definition, traveling into the exact set of conditions that just proved capable of destroying a competent crew, usually in a hurry, usually with less preparation, and often in worse weather, because time has passed. In an ordinary place, rescuers accept elevated risk. In the top of the Labrador Sea and on the ice that borders it, the rescuers are exposed to the identical hazard at the identical intensity, and the record shows it killing them at a rate that in this case matched and exceeded the original event. There is one more thing in this story, easy to miss, and it points in Marinsins directly at what comes next. Every part of that 6-month operation depended on weather information, and every decision, when to fly, when to try a landing, when to keep the aircraft on the deck, was made against a forecast. Whoever had the better picture of what the atmosphere over the Labrador Sea and Greenland was about to do had a decisive operational advantage, in rescue and in war. Somebody else had worked that out. And in the autumn of 1943, they came to Labrador to do something about it. On the 18th of September 1943, the submarine U-537 sailed from Germany under Kapitän Leutnant Peter Schruve. She was not hunting. Her cargo included a set of sealed steel canisters and 2 civilians, Dr. Kurt Sommermeyer, a meteorologist from Siemens, and his assistant Walter Hildebrandt. She crossed the Atlantic, went north past Newfoundland, and on the 22nd of October 1943, dropped anchor in Martin Bay at the northern tip of Labrador, a place with no settlement, no garrison, no shipping, and no reason for a German submarine to be there. For the next 48 hours, the crew worked. The canisters weighed around 100 kilograms each and had to be manhandled into rubber boats, rowed ashore through cold water in a bay on the outer Labrador coast in late October, and then carried inland and uphill. They set the equipment up roughly 400 yards from the shore on a hill about 50 meters high. They assembled a mast, connected batteries, and switched it on. The device had a designation, Wetterfunkgerät Land 26, and a name, Kurt. It was an automatic weather station. It read pressure and temperature and transmitted the values by radio on a schedule every few hours with no human being present. Nobody stayed behind. The submarine finished the job, weighed anchor, and left. Before they went, they took some trouble to make the installation look like it belonged to somebody else. Accounts of the site describe empty American cigarette packets scattered around and markings suggesting a Canadian meteorological service, a disguise for observers who, realistically, were never going to come. Now stop and consider what that operation cost. In October 1943, the Battle of the Atlantic had turned hard against the U-boat arm. Losses were severe. Boats were being sunk faster than they could be replaced, and every submarine at sea was a scarce asset that could be sinking merchant tonnage. Germany took one of them, gave it a 2-month round trip across a contested ocean, sent 2 scientists along, and spent 48 hours anchored and immobile on an enemy coastline, the most vulnerable state a submarine can be in order to install an unmanned instrument on a hill in northern Labrador. You do not do that for a marginal advantage. You do it because you have concluded that the atmospheric conditions on this particular coast are worth a submarine. The reasoning is simple, and it is the single most important reframing in this story. Recall which way the weather runs across this ocean. The same fact that left those ferry pilots flying downstream of conditions nobody could see forming. Whoever holds the western side of it is upstream, and being upstream means seeing the weather before it arrives. Britain, Canada, and the United States had observers across North America, across Greenland, on ships, on Iceland, the whole upstream field. Germany had almost nothing west of Norway, which meant German forecasters were reading a chart with the left-hand side torn off, trying to predict conditions over Europe and the Atlantic without knowing what was already forming over the Labrador Sea. And the systems that would arrive over Britain, over the convoy routes, over the invasion beaches, were in many cases assembling right there, over the basin, out of the ocean's own heat, in the way described earlier. Cold Canadian air over warm subsurface water, a low deepening explosively. The whole thing then sliding east across the shipping lanes. A forecaster with Labrador pressure readings has 3 or 4 days of warning about a storm that a forecaster without them will meet as a surprise. That is what Kurt was for. It is also the most compact possible proof of something this documentary has been building toward. The Labrador Sea is not a remote backwater where bad weather happens to occur. It is a generator. It manufactures conditions and exports them. And by 1943, both sides of the largest war in history understood that well enough to fight over the data. The station itself failed almost immediately. It ran its scheduled transmissions as designed for a short time. Within days, the signal degraded, and by the middle of November, it had gone silent. Whether that was battery performance in the cold, an antenna problem, interference, or something else, is not conclusively established. The outcome is not in doubt. A purpose-built, expensively delivered automatic instrument, placed by specialists, lasted a matter of weeks on that coast before the environment stopped it. That deserves a moment, because it is a pattern. This region does not merely endanger people. It reliably breaks unattended machinery, and it does so through accumulation rather than drama. Cold degrading batteries, ice loading an antenna, wind fatiguing a mast, salt working into contacts. There is nobody to fix it. The reason Kurt was automatic in the first place is that no crew could be supplied there. The reason it failed is that no crew was there to fix it. The remoteness that made an automatic station necessary is the same remoteness that made it useless. Then the strangest part, nobody noticed. The station sat on that hill for decades, not hidden, not buried, standing on a hillside in northern Labrador with a mast on it. Canada did not know it was there. The war ended, the Cold War started, the Labrador coast was overflown thousands of times, and the equipment stayed where the Germans had left it. U-537 did not survive the war either. She was lost in November 1944 in the Java Sea, sunk with all hands, so the crew who could have told anyone were gone. The story came out through paperwork, in a way that would have pleased Selma Barkham. In the late 1970s, a retired Siemens engineer named Franz Selinger began writing a history of the German Weather Service. And while going through Sommermeyer's surviving papers, he found photographs of a weather station and a submarine that did not match any of the known installations in the eastern Arctic. He worked out roughly where they must have been taken. He contacted Alec Douglas, a historian with the Canadian Armed Forces, and in 1981 an expedition went to Martin Bay and found it: canisters, mast components, the remains of the installation. On the hill, where U-537's crew had left it 38 years before. The material was recovered and is held in Canada as a museum collection. There is a fair argument made in Labrador and reported in the northern press that people in the region had come across the site before its formal identification, and that the 1981 expedition was a confirmation rather than a discovery. That distinction is worth stating honestly because it fits the wider pattern in this basin. The people who live on a coast usually know what is on it, and the record only registers a thing when an institution goes and writes it down. So by the end of the Second World War, the strategic value of Labrador sea weather data was established beyond argument by both sides, at real cost. The question that follows is obvious. If knowing what this basin is doing is that valuable, and if an unmanned machine cannot survive out there, what do? You put people in it, permanently, on purpose, in the middle. The idea had actually started before the war. In 1940, Franklin Roosevelt ordered Coast Guard cutters on neutrality patrol off the Grand Banks to take up fixed positions and report the weather. And in February of that year, the cutters Bibb and Duane anchored the concept in practice. After 1945, it was formalized into an international system under the North Atlantic Ocean Stations Agreement, with participating nations funding a grid of manned positions across the ocean, each one identified by a letter. One of them was Bravo. Its position was 56 degrees 30 minutes north, 51 degrees west. Put that on the chart of everything described so far, and it lands in the middle of the Labrador Sea, not near the edge. In it, over water around 3,500 meters deep, several hundred kilometers from the Labrador coast and several hundred from Greenland, in the part of the basin where the convection happens, downwind of the cold air outbreaks, in the stretch of ocean where the weather is built rather than merely passing through. A ship was stationed there, more or less continuously, from the mid-1940s until 1974. Understand what that job actually was? Because it is one of the strangest jobs in the history of seafaring. The vessel was assigned a small box of ocean and required to stay inside it, not to transit it, to occupy it. Surface observations went out every 3 hours at fixed times keyed to Greenwich. Midnight, 3, 6, 9, and so on around the clock every day for the length of the patrol. Between them, the crew launched radiosondes, hydrogen or helium balloons carrying a small instrument package that transmitted temperature, pressure, and humidity as it climbed, giving a vertical profile of the atmosphere that nothing else could provide. The ship also served as a radio beacon and position reference for aircraft crossing the Atlantic, and as a permanent search and rescue asset in a piece of ocean where there was otherwise nothing. Patrols ran on the order of a month before relief, roughly 35 days on station. Now apply the machine described earlier to a ship whose orders are to stay put. Every other vessel in this story had a storm plan, and every storm plan reduces to the same thing: be somewhere else. Change course, run off, seek shelter, alter the schedule. A weather ship cannot do any of it. The value of the data depends entirely on it coming from the same coordinates, at the same times, without gaps. Leaving the box is the one thing the ship exists not to do. So when a low deepens explosively over the Labrador Sea in February, the weather ship's response is to reduce speed, come around to the most survivable heading, and hold position inside it while continuing to file observations every 3 hours. And the observations do not file themselves. Somebody has to go out on deck in that. A radiosonde launch is a physical, two-handed job, inflating a balloon, attaching the instrument, releasing it cleanly without letting it foul on the rigging. Performed on a steel deck that is pitching, in the dark, in wind, with spray freezing on everything it touches. In icing conditions, the same crew that is chipping ice off the rails to keep the ship upright is also expected to keep launching balloons on the hour. The men on those patrols were, in a very literal sense, employed to stand inside the storm and describe it. The reason anyone paid for this was aviation, and there is one incident that shows exactly why. On the 13th of October 1947, a Boeing 314 flying boat called the Bermuda Sky Queen left Foynes in Ireland for Gander in Newfoundland with 62 passengers and 7 crew. She met gale force headwinds across the Atlantic. Somewhere past the halfway point, her captain did the arithmetic and got an answer that has no good version. Not enough fuel to reach North America, and not enough to go back. What saved 69 people was that he knew where a ship was. The Coast Guard cutter Bibb was on Ocean Station Charlie. He turned around, flew several hundred kilometers back east to reach her, and homed on her radio beacon. The seas were running about 20 feet, kicked up by the same wind that had emptied his tanks. Bibb pumped oil onto the water to knock the tops off the sea, and the aircraft ditched. The cutter's boats took every person off, which is the Ocean Station system working exactly as designed, and a fair reminder that this network was not an abstraction. It was a set of ships parked in the empty parts of the ocean so that the empty parts would stop being empty. Bravo was the one parked in the worst of them. And while the crews were doing the job they were paid for, they were doing something else that nobody had planned for. Alongside the atmospheric work, the ships took oceanographic measurements, lowering instruments and sample bottles down through the water column to record temperature and salinity at depth. Same position, same instruments, over and over for the better part of a quarter of a century. Nothing like it existed anywhere else in this ocean. What accumulated at Bravo was a continuous, deep, single-point record of the interior of the Labrador Sea across 24 years, taken by hand, in weather that was frequently trying to sink the platform doing the taking. When oceanographers went through it properly, the analysis by the Canadian scientist John Lazier, published in 1980, is the reference point. The record showed something remarkable. In winter, the temperature and salinity profile at Bravo would go vertical. The distinctions between the surface layer and the water hundreds of meters down would collapse, because the surface water had become dense enough to sink and the column had overturned. Deep convection, happening in the open ocean, at that spot, in the winters those crews had been sitting through. The water they were being thrown around on top of in February was, at that moment, descending past 1,000 meters and heading for the deep Atlantic. The record showed something else, and this is the part that reaches into the present. It showed the process stopping. Between roughly 1968 and 1971, the deep convection at Bravo shut down. The cause, as later work established, was a body of unusually fresh water that spread through the northern North Atlantic in those years. The event that became known as the Great Salinity Anomaly. Fresh water is light. A fresh layer sitting on top of the basin acts as a lid, and the surface can be cooled hard all winter without ever becoming dense enough to sink through it, because salinity, not just temperature, controls density in this ocean. The atmosphere kept doing its part. The convection stopped anyway. Remember that mechanism. A thin layer of fresh water at the surface can switch off the deepest overturning in the North Atlantic. It matters enormously later, and the only reason anybody could see it happen is that there had been a ship sitting in that exact spot with a wire and a set of sample bottles for 24 years. In 1974, Ocean Station Bravo was discontinued. The reasons were the usual ones, and they were not unreasonable. Satellites were beginning to provide broad-scale atmospheric data. Long-range aircraft no longer needed a surface ship as a navigational stepping stone. Keeping a manned vessel on that station year-round is expensive, and the cost is paid in fuel, in hulls, and in cruise time in a place that is hard on all three. The consequence was that the single best long-term instrument ever placed in this basin was switched off, and the continuous record ends. Everything after that had to be reconstructed from research cruises that visit for a few weeks, from moorings that record but cannot be repaired midwinter, and eventually from robots. There is a tidy irony in that, and it is not a comfortable one. The weather ships were put out there for safety, to warn aircraft and shipping about the conditions this basin was generating. They ended up producing the only long baseline anyone has for how the basin's deep circulation actually behaves. And they were withdrawn about a decade before the questions that data answers became some of the most consequential in climate science. One more thing about that era, and then we go back to the water. In January 1959, the Ocean Station network was still running. There were cutters of the North Atlantic Weather Patrol type operating in these waters. There were trawler fleets working the Greenland banks. There were radio watches being kept on both sides of the ocean. And there was, for the first time in history, a reasonably good chance that a distress call from the middle of this basin would be heard by somebody with a ship. Denmark had just built a vessel designed on exactly that assumption. To understand why the Hans Hedtoft existed, you have to understand what had just happened to Greenland's legal status. Until 1953, Greenland was a Danish colony, run as one, supplied on a colonial schedule, which in practice meant ships in summer and silence in winter. In 1953, the Danish constitution was amended, and Greenland ceased to be a colony and became an integral part of the Kingdom of Denmark. Greenlanders became Danish citizens with representation in the Danish parliament. That is a legal change with a physical consequence, and the consequence lands on the Labrador Sea. If Greenland is a colony, a 5-month gap in communications is a cost of empire. If Greenland is part of Denmark, a 5-month gap is a 2-tier country. Citizens do not accept being unreachable for the winter. Mail should move. Officials should travel. Business should function. Someone who needs to get to Copenhagen in February should be able to get to Copenhagen in February. The political logic of integration demands a year-round link, and there are exactly 2 ways to provide one across that water: aircraft or ships. In November 1958, the airfield at Narsarsuaq, the old wartime Bluey West 1, at the head of its fjord in southern Greenland, was closed. Whatever the reasoning at the time, the operational effect is stark. The air option went away, and it went away weeks before the ship's first voyage. Whatever load the route was going to carry that winter, the ship was going to carry it. She was built in 1958 at Frederikshavn in northern Denmark and named for Hans Hedtoft, the Danish prime minister who had driven the Greenland reforms and who had died in 1955. She was not large, about 83 meters, a little under 3,000 gross tons, motor-driven, with accommodation for around 60 passengers and 40 crew. She was operated by the Royal Greenland Trade Department, the state body that ran the Greenland Connection, and she was, for her size and for her trade, a serious ship. She had a double bottom. She was divided into 7 watertight compartments so that flooding in one part of the hull would not automatically flood the rest. Her bow and stern were reinforced for working in ice. She was, in short, designed by people who had thought carefully about the specific hazard everyone associates with these waters, hitting something hard, and who had built in the specific countermeasures that engineering can offer against it. Every one of those features is a real improvement, and each solved a real problem. Reinforced ends let a ship push through young ice and survive contact that would open a normal hull. A double bottom protects against grounding damage and against ice working along the underside. Subdivision buys time. It converts a hole from an immediate sinking into a survivable casualty, provided the damage stays inside the compartments it was designed for. Notice what that list does not contain. It contains nothing that reduces the heat flux off the Erminger water, nothing that stops a low from deepening explosively overhead, nothing that softens the sea when wind opposes the current over a shelf edge, nothing that prevents spray from freezing above the center of gravity, and nothing whatsoever that changes the distance from that stretch of ocean to the nearest place that could send help. The improvements were all in the category of surviving contact. The mechanism that actually governs this basin is in the category of everything else. There is one further design detail that became contentious afterwards. The hull was riveted rather than welded, and critics argued that riveted construction was less able to withstand ice impact than a welded hull of the same scantlings. That criticism is on the record, and it belongs in the account, but it belongs there honestly. What happened to that ship is not established in enough detail to attribute it to construction method, and nobody has ever examined the wreck, because nobody has ever found it. She sailed from Copenhagen on the 7th of January 1959. The outbound voyage went well. She called along the Greenland coast, Nuuk, Sisimiut, Manitsoq, and reached Julianahaab in the south. Reports at the time noted she had made the crossing in record time. Her master was Poul Ludvig Rasmussen, 58 years old, a career officer in the Greenland trade. He was quoted at the time describing what the ship represented: a revolution in Arctic navigation. Read that against her specification, and it is not a boast. It is a fair professional summary. A reinforced, subdivided, powered vessel had just crossed to Greenland and worked the coast in January faster than anything before her, and the man who had taken her there was saying what everybody in the trade could see for themselves. The trouble is what a sentence like that does once it leaves the bridge. A new vessel, completing a difficult winter passage faster than anyone previously had, is exactly what everyone had hoped for. It is proof of concept. It is the thing that gets written up. And it is the thing that quietly recalibrates what the route is expected to deliver. A record on the first attempt does not only demonstrate capability, it sets an expectation. And on a scheduled service, expectations turn into schedules. On the 29th of January 1959, she left Julianahaab for Copenhagen. Aboard were 40 crew and 55 passengers, 95 people. They were not adventurers. This was a scheduled service. And the passenger list was the passenger list of a working country in winter. Officials, families, people traveling for medical reasons, people going home. Among them was Augo Linge, a Greenlandic teacher and writer who had been one of the first 2 Greenlanders elected to the Danish parliament. A man whose entire public life had been about Greenland being treated as a full part of the kingdom, traveling on the ship that had been built to make that true in January. In the holds was frozen fish, which was Greenland's export, and the economic reason the run made sense at all. And there was one other item of cargo, and it is the detail that has stayed with Greenlanders for 3 generations. She was carrying roughly 3¼ tons of archives, historical records of Greenland, including church registers, being moved to Denmark, baptisms, marriages, deaths, the written memory of communities along that coast, packed in crates, in the hold of a ship leaving in a January gale. The route out of Julianahaab runs south and then east around Cape Farewell. By now you know what that corner is. It is the place where an ice dome 3,000 meters high deflects and accelerates the westerly flow, where the tip jet forms, where the warm Erminger water comes around from the east and the cold outflow comes down from the west, and where the icebergs calved from Greenland's glaciers are carried in numbers by the current. There is no way from southwest Greenland to Denmark that does not go past it. It is not an optional hazard on that route. It is the route. The weather was bad. Not unusual for the last day of January in that place, and not, by itself, a reason for a ship of her design and purpose to be anywhere else. This was precisely the condition she had been built for. And the crew were experienced in the Greenland trade. At around 10 minutes to 2 in the afternoon, on the 30th of January 1959, the Hans Hedtoft transmitted that she had struck an iceberg. Her reported position was 59 degrees 30 minutes north, 43 degrees west, roughly 35 nautical miles, about 65 kilometers, south of Cape Farewell. The message was calm, and it was clear, and it went out immediately. There was no confusion about who she was, where she was, or what had happened. And that is the moment where this stops being a story about a ship hitting ice and becomes a story about what a correct distress call is actually worth in the middle of the Labrador Sea. Start with the thing she hit, because people picture the wrong object. The iceberg in the popular imagination is a white cathedral. Visible for miles, the sort of thing a lookout would have to be asleep to miss. Those exist, and they are, in practice, among the least dangerous ice in the ocean, because they are enormous and obvious, and both radar and eyes find them easily. The ice that sinks ships is the small stuff. Icebergs decay, and as they decay, they shed pieces. And those pieces have their own names in the trade. Bergy bits, roughly the size of a house, and growlers, roughly the size of a car or a truck. A growler floats with only a meter or so showing. It is wave-washed, so its exposed surface is wet and smooth and dark rather than white. In a running sea, it is indistinguishable from a breaking crest, and it is not soft. This is glacial ice, snow compressed under its own weight over thousands of years, squeezed until the air is driven out of it, dense and hard. It is not the sea ice that freezes on the surface each winter and crushes when a strengthened bow leans on it. A growler the size of a small car has a mass measured in tons, and around 9/10 of that mass is below the waterline, where it can meet a hull below the ice belt, below the reinforced band, in the plating that was never designed for impact. Now the detection problem, which the Danish inquiry afterwards went straight to. Radar in 1959 was genuinely useful, and it was on ships in these waters, and it had a specific, well-understood weakness. Small targets low in the water, in a rough sea, get lost in sea clutter. The radar return from wave tops fills the near part of the screen with noise, and a growler's echo is small, intermittent, and sitting inside that noise. The heavier the sea, the worse it gets, which means the detection failure is at its maximum precisely when the sea state is at its maximum, which is precisely when a ship is least able to avoid anything. Visual lookout in that situation is worth almost nothing. It was the last day of January at nearly 60 degrees north in a gale, with spray coming over. Daylight that far north at that date is short, and by mid-afternoon, it is going. A lookout facing into freezing spray and failing light, looking for a dark, wet object a meter high among breaking crests, is not going to find it. So the strike itself was, in the honest sense, close to unavoidable at that time by that technology. The inquiry said as much. That is not an excuse. It is the identification of a gap that no amount of hull reinforcement addresses, because it is a gap in seeing rather than a gap in strength. At 13:56, the distress went out. What follows is one of the very few sequences in this story that can be watched on a clock message by message as the doors close. Within about an hour of the impact, a second transmission reported the engine room flooded. At 15:12, she reported that she was sinking. At 17:41 came a message that she was sinking slowly and needed immediate assistance. At 18:06, the beginning of an SOS was received. After that, nothing. A note on those times because it matters for trusting them. Contemporary press reports of 1959 carry the same sequence about 2 hours earlier, since the accounts do not all use the same time reference. The order of the messages and the gaps between them are consistent across sources, and the gaps are the part that decides everything. Take the second message. A flooded engine room undoes the ship's entire safety architecture, and the reason is specific. 7 watertight compartments are a defense against sinking, and they work, provided the flooded compartments are ones the ship can survive losing. The engine room is not one of those compartments in any useful sense because it does not merely contribute buoyancy, it contains the machinery. Lose the engine room, and you lose propulsion, which means you lose the ability to keep the bow into the sea. A powered ship in a gale survives by pointing at it. An unpowered ship falls off, lies beam on to the swell, and begins rolling through her whole range with every wave. You also lose main electrical power, which means pumps, steering gear, and heating. You lose the capacity to move toward help or away from ice. You lose the ability to hold a position, which matters enormously for anyone trying to find you, because a disabled ship in a Cape Farewell gale does not stay where she reported. From that point, the vessel is not a ship anymore in the operational sense. She is a drifting object with 95 people inside her. And now the part that should genuinely disturb you, because it inverts the assumption every one of us carries about modern disasters. She did not sink quickly. The radio kept working the whole time. 4 hours and 10 minutes separate the first distress call from the last broken transmission. In most maritime emergencies, 4 hours is an enormous gift. It is enough to muster, to prepare boats, to get survival gear on people, to organize, to keep everyone informed. It is enough for a nearby vessel to close a substantial distance. 4 hours is very often the difference between everyone living and everyone dying. Here it was not enough, and the reason has nothing to do with the ship and everything to do with the map. Follow the rescue as a physical sequence rather than as an outcome. The signal was received. That worked. The radio watch system across the North Atlantic did exactly what it had been built to do, and the position was known and the identity was known. Assets were identified and directed. The United States Coast Guard cutter Campbell was ordered to the position from a long way off. 2 West German trawlers working the Greenland grounds turned toward her, and one of them was not far away at all. The Johannes Kruse, out of Bremerhaven, was about 25 miles east of the position the Hans Hedtoft had given. 25 miles. Some 45 kilometers. On a decent day, that is 3 hours steaming for a working trawler, and she turned toward it immediately. Set that against 4 hours and 10 minutes of radio traffic, and on paper, it should have worked. It did not. And the reasons are the ones this basin has been handing out since the 16th century. A trawler driving into a subpolar gale is not making her calm water speed. She has to come down or she breaks something. Punching into a heavy head sea can cut a working vessel's speed by half or more. The sea that afternoon was running around 20 feet, and the Kruse was pushing through snow squalls, which meant that for long stretches of the approach, her people could see almost nothing. And she was not steaming toward a fixed point. She was steaming toward a set of coordinates that a ship without engines had transmitted, and a ship without engines drifts. Pushed by wind and swell, and by the current running through that corner of the ocean. The longer the approach took, the further the casualty was from the number in the message. Every hour of delay made the search area bigger, and the search area was growing in the dark. The Campbell, meanwhile, had a long distance to cover across water in the same condition. Those are the distances that have been sitting under this entire story. Hundreds of kilometers, with nothing in between. While they steamed, the light went. By around 4 in the afternoon local time at that latitude and date, useful daylight was finished. Everything after that was a search in darkness. And then there was the ice. The reason she was in trouble was that there was glacial ice in the water, and the vessels going to help had to enter that same water. At night, in a gale, at whatever speed they could manage, looking for a drifting casualty. The rescuers were being sent into the exact hazard that had caused the casualty, with worse visibility than the casualty had enjoyed when she hit it, and with the same radar limitations against the same small targets. Neither vessel reached the position before she went down. The record is explicit about the reasons: rough seas, floating ice, failing daylight, poor visibility. And there is one more detail in the radio log that is worth sitting with. That final fragment at 1806, the start of an SOS that stopped, was picked up by the Johannes Kruse. The nearest ship in the ocean, the one closing the distance, 25 miles out and still coming, was the one listening when the transmissions ended. The Campbell's assessment of the conditions on the 31st of January has been reported ever since, and it comes from a ship with a serious pedigree. Her people described what they were in as worse than anything the ship had experienced on transatlantic convoy escort duty during the Second World War. That is a cutter's crew comparing a Labrador sea gale to the winter North Atlantic in wartime, and putting the Labrador Sea first. The search continued. Ships and aircraft worked the area for over a week. It was called off on the 7th of February, 1959. They found nothing. No boats, no rafts, no bodies, no debris field. 95 people. A ship of nearly 3,000 tons. And the ocean returned absolutely nothing. 8 months later, on the 7th of October 1959, a lifebuoy marked with her name washed ashore in Iceland. It is the only piece of her ever recovered. The accounts are not perfectly consistent. Most place the find in Iceland, one puts it in the Faroes, and at least one contemporary source speaks of 2 rings rather than 1. But the essential fact is not in dispute. A life ring carried east from Cape Farewell by the current system that runs across toward Iceland came ashore on a beach the better part of 2,000 kilometers from where she was lost, 8 months after the fact. The wreck has never been found. There is no wreck site, no survey, no debris analysis, no forensic account of how she went down. What sank her beyond the initial impact? Progressive flooding, a shift of cargo, loss of stability, a structural failure. The sea getting into her through damage that the compartments could not contain is not established and will probably never be established. The honest statement is that a ship reported striking ice, reported flooding, transmitted for 4 hours, and then stopped, and everything after that is inference. What Denmark did afterwards is instructive, because it is one of the few places in this story where an institution looked at the mechanism rather than the object. The inquiry did not conclude that the answer was a stronger ship. It went to the detection gap, the inherent limits of the radar of that era against growlers and small ice in variable sea states and poor visibility. And the recommendations that followed were about information rather than steel. Dedicated ice reconnaissance for Greenland waters and systematic reporting of what was found. Danish ice observation services were formalized on the back of it. And then Denmark did the other thing, the one that connects directly back to a decision made by Basque ship owners 400 years earlier. It stopped sending passenger ships across in winter. Narsarsuaq, the airfield that had been closed in November 1958, was reopened. The winter link to Greenland moved into the air, where the aircraft could go over the top of the mechanism instead of through it, and where a flight that cannot be made safely can simply be canceled and flown tomorrow without anyone sitting out on that water while the decision is made. That is the reversal, and it is the hardest one in this story to accept. Everything technological worked. The hull was strong. The subdivision was real. The radio was excellent. The distress call was received cleanly across an ocean. The position was accurate. The identity was certain. And the response was launched promptly by competent professionals who then drove their own ships into a Cape Farewell gale at night to try to reach her. The only thing that failed was arrival. Communication had been transformed over the previous half-century. Distance had not moved a meter. And in the middle of the Labrador Sea, in winter, distance is the entire problem, because everything else in the system, the storm, the ice, the sea state, the darkness, the drift, is working to make sure that whatever help is coming is too far away, too slow, and running out of light. She is generally described as the last ship sunk by an iceberg with loss of life. On the 30th of January 2005, Queen Margrethe unveiled a memorial in Copenhagen to the 95, and the archives went to the bottom with them. 3¼ tons of parish records, the baptisms, marriages, and deaths of Greenlandic families going back generations. There is no copy. For a great many people in Greenland, the reason they cannot trace their own family beyond a certain point is that the paperwork was in the hold of that ship. The Labrador Sea did not only take 95 lives that afternoon, it took the record of thousands of others. 12 years after the Hans Hedtoft in 1971, a drilling rig spudded a well called Leaf E38 on the Labrador Shelf, and the industrial era in this basin began. The reason was gas. Through the 1970s, a run of wells went down along that shelf. Bjarni H81 in 1973 and 1974, Herjolf M92 in 1976, Hopedale E33 in 1978, Turk P100 in 1979, Snorri, Gudrid, and several of them found substantial quantities of natural gas. The Bjarni complex alone is estimated to hold more than 3 trillion cubic feet. Every one of those discovery wells was subsequently abandoned because the industry at the time was hunting oil, and because getting gas out of the Labrador Sea and to a market is a problem that has still not been solved commercially. What is interesting is not the geology. It is how they drilled at all. The first attempt in 1971 used a conventional anchored vessel. It did not work. And the reason it did not work is the most concise statement anyone has ever made about operating in these waters. An anchored rig cannot move. A drilling vessel held by anchors is committed. Getting it off location takes many hours and a lot of deck work. That is fine in the Gulf of Mexico. On the Labrador Shelf, where icebergs come down the current in numbers and where the weather assembles overhead, a vessel that needs half a day to leave is a vessel that will eventually be somewhere it cannot leave in time. The breakthrough came in 1973 and 1974 with a dynamically positioned drill ship called Pelican. Dynamic positioning means the vessel holds its own station using thrusters under computer control, reference to acoustic beacons on the seabed. It is not tied to anything. It can disconnect from the well, move off location, wait, and come back, which is a genuinely strange thing to have built and worth saying out loud. The technological advance that finally allowed people to work the Labrador Sea industrially was not a stronger structure or a better hull. It was a better ability to run away. That principle has governed everything offshore in these waters since, and it has produced an entire discipline: ice management. Standby vessels track icebergs by radar and by air, model their drift, and when one is projected to come too close, they physically try to change where it goes. The primary method is towing, running a rope around the berg and pulling it onto a different heading. Smaller pieces can be pushed with propeller wash or broken up with water cannon. If none of that works, the rig disconnects and moves. The tow rope method sounds crude, and it is, and it was arrived at by elimination. Through the 1980s, the industry tried nets, a series of prototypes with names like the Merex Growler Net, the Acadian Ice Net, the Esso Experimental Growler Net, the Dobrocki Sea-Tech Ice Arrestor. Reviews of that work, including by the Newfoundland Research Center Sea Corps, found that the nets mostly failed for practical reasons. They were too small for the bergs that mattered, and the bridle arrangements let the net slip off. So the industry went back to a rope, a big engine, and enough advance warning to make the geometry work. Which is the point. Ice management is not iceberg control. Nobody stops an iceberg. A mass of glacial ice can run to hundreds of thousands or millions of tons, driven by current and wind, and no vessel afloat is going to overpower it. What ice management does is by angles. Nudge the drift a few degrees, days out, so that the berg passes rather than arrives. It works because of forecasting and because of time. Take away the time, and it stops working. And the thing that takes away time is the same thing it has always been: small ice in a rough sea, in poor visibility that nobody sees until it is close. Modern marine radar is far better than 1959 radar, and it still degrades against growlers and heavy clutter. The International Ice Patrol, created in the aftermath of the Titanic, which was sunk by a berg that had calved off Greenland and been carried south by the Labrador Current, exactly the same conveyor described earlier, still flies aircraft over this water every season because looking remains a necessary part of knowing. Greenland's glaciers shed roughly 40,000 icebergs a year into these waters. The great majority melt, ground, or break up long before they matter to anybody. A small fraction make the entire journey, north up the West Greenland coast, around the top of Baffin Bay, then south down the Labrador side on the current. And those are the ones that turn up where ships are. In 2017, the Ice Patrol counted 1,008 icebergs drifting far enough south to enter the transatlantic shipping lanes. That was the fourth consecutive season classified as extreme. Analysts attributed the numbers to a combination of powerful storms moving ice south and elevated calving from Greenland's retreating glaciers. More than 1,000 pieces of glacial ice in the lanes in 1 year in the 21st century. Set beside that the state of rescue, which is the other half of every equation in this story. Communication has been effectively solved. A vessel in trouble anywhere in the Labrador Sea now has satellite voice and data, an emergency beacon that transmits an identity and a position to a satellite constellation, and an obligation under international convention to carry equipment that makes a distress alert essentially automatic. The Hans Hedtoft had to have a radio operator send a message that someone had to be listening for. A modern casualty does not. The alert goes out whether anyone is conscious or not, and it goes out with coordinates. So the recognition stage of a rescue, which used to be uncertain, is now close to instant. Everything after recognition is still governed by the map. On the Canadian side, the primary helicopter response for this region comes from 103 Search and Rescue Squadron at 9 Wing Gander in Newfoundland, which operates a small number of CH-149, which CH-149 cormorants, and is responsible for an area that includes the offshore waters of Canada's Atlantic Exclusive Economic Zone. Crews there routinely find themselves working the better part of 200 miles offshore, and the arrival of offshore oil production brought with it the possibility of refueling at a platform, which genuinely extends how far a helicopter can go and still come back. 200 miles is a long way. It is also nowhere near the center of this basin. Ocean Station Bravo sat roughly 300 nautical miles, some 550 kilometers, off the Labrador coast, and about the same again from the nearest point of Greenland. On the Greenland side, the Danish Joint Arctic Command in Nuuk is responsible for a maritime area of extraordinary size with a small number of assets. The result is a straightforward geometric fact. There is a large body of water in the center of this basin where no helicopter is going to arrive, in any weather, on any day, because it is simply beyond the reach of the aircraft based on either side. For that water, rescue means a ship, which means hours or days, not minutes. Or it means an aircraft that can drop equipment and observe but cannot land or lift anyone, and then apply the weather. Because rescue capability is not a constant. It is a function of conditions. And the conditions that generate casualties in this basin are precisely the conditions that suppress rescue. A helicopter cannot hoist in the worst sea states. The aircraft has to hold a stable hover over a deck or a raft that is moving vertically through many meters while the aircraft itself is being hit by the same wind. Icing is an absolute constraint for rotorcraft. Ice on a rotor blade changes its shape and therefore its lift, and it does not shed evenly, which produces vibration and asymmetry that can end a flight. So the icing conditions that are steadily loading a fishing vessel's rigging and eroding her stability are the same conditions that keep the helicopter that would rescue her crew on the ground. A fixed-wing aircraft can fly higher and go further and find people. It cannot pick them up. A ship can pick them up and cannot get there quickly, and if it does get there, it arrives into the same sea that caused the emergency, which is exactly where the Johannes Kruse and the Campbell were in 1959. And exactly where John Pritchard and Benjamin Bottoms were in 1942. That is the hard, unglamorous shape of the modern situation, and it deserves to be said without drama. everything about knowing has improved almost beyond recognition. Almost nothing about reaching has improved at all. And the gap between those two curves is where people in this basin still die. There is one more actor in the modern Labrador Sea, and it is the strangest of all, because it went back into the middle of the basin on purpose. In winter, knowing everything in this story. On the 2nd of February, 1997, the research vessel Canour went into the Labrador Sea and stayed until the 20th of March. Not the edge of it, through it. Over the 6.5 weeks of that cruise, the ship occupied 127 hydrographic stations across the basin, working through the worst part of the year deliberately, as the first field phase of the Labrador Sea Deep Convection Experiment. Understand what a hydrographic station actually is, because the number 127 is meaningless until you do. The ship stops. A frame carrying instruments and a ring of sampling bottles. A CTD rosette, a couple of meters across, heavy, is lifted off the deck by a crane and put over the side. It goes down on a wire, sometimes 2,000 or 3,000 meters, recording conductivity, temperature and depth continuously, and bottles are triggered at chosen depths on the way back up. The whole cycle takes hours. Then the frame has to be recovered, which means bringing a heavy swinging object back over a rail and onto a pitching deck, and then the bottles have to be drained and the samples processed, and then the ship moves to the next position and does it again. 127 times. In a Labrador Sea winter, on a deck that is icing, in a basin where a low can deepen explosively overhead in a day, and where the Cape Farewell jet is running. The published accounts of that cruise describe the working conditions as extremely difficult, which is oceanographer for something considerably stronger. They got what they came for. The 1997 winter was moderate rather than extreme, but the water column had been preconditioned by several hard winters before it, and the forcing that did arrive was enough to drive convection to around 1,500 meters. They watched it happen. They measured the column overturning while sitting on top of it. Why does anyone accept that risk? Because of what this basin does for the rest of the planet. When surface water here becomes dense enough to sink, it takes with it everything dissolved in it, including oxygen and including carbon dioxide absorbed from the atmosphere, and delivers it into the deep interior of the Atlantic, where it stays for a long time. That process is one of the few places where the deep ocean is directly connected to the air. It is a component of the overturning circulation that moves heat around the Atlantic. The physics that kills people in this basin is the same physics that ventilates an ocean, and there is no way to study it from a distance because it happens in winter, at the surface, in the middle, in exactly the conditions that make being there dangerous. After 1997, the field made a decision that is quietly one of the most honest admissions in this entire story. It stopped sending ships to stay. The Labrador Sea is now monitored primarily by machines. Argo floats drift at depth, sink to 2,000 meters on a schedule, rise while recording a profile, surface, transmit to a satellite, and go back down. For years, unattended, through every storm, in the dark, in February, in the middle, moored instruments sit on the bottom on chains and record. Autonomous gliders fly slowly through the water column on changes in buoyancy. Since the summer of 2014, an international observing array called OSNAP has run a line of moorings and instruments across the subpolar North Atlantic to measure the overturning directly. Every one of those systems exists because a human being cannot be there. Not should not. Cannot, not affordably, not safely, not continuously. 250 years after the Moravians settled on one sailing a year, and 50 years after Ocean Station Bravo was withdrawn, the operational conclusion about the middle of the Labrador Sea in winter is unchanged. Send instruments. Do not send people. And the instruments have been recording something that keeps changing shape. Through the mid-2010s, the basin convected hard. Argo and ship data show the strongest winter surface heat loss of the entire 1994 to 2023 record occurring in 2015, with mixed layers reaching 1,500 to 2,000 meters in 2015 and 2016, a peak mixed-layer depth of around 2,100 meters in 2016, and the deepest convection of the 1996 to 2023 record occurring in 2018. Each strong winter preconditioned the next, stripping away the stratification so that the following year needed less forcing to reach the same depth. Then, it stopped. In the years since, the basin has warmed and freshened at the surface, and deep convection has essentially ceased, and a fresh, buoyant surface layer is the reason. The same mechanism that the Bravo record caught between 1968 and 1971 during the Great Salinity Anomaly. Be careful here. The certainty ends at a specific place, and the place should be marked. What is measured is not in serious dispute. The heat content and salinity of the basin, the depth to which it mixed each winter, the timing of the shutdown, the decline in sea ice extent and duration, the increase in Greenland's meltwater discharge, and the iceberg counts. Those are observations. What is genuinely contested is what they mean for the bigger circulation. For decades, the Labrador Sea was assumed to be the main engine of Atlantic overturning variability. The direct measurements from OSNAP challenged that assumption hard, indicating that the eastern basins, the Erminger and Iceland basins, accounted for far more of the variability than the Labrador Sea did. That is a real scientific reversal, published and argued over, and it is still being reconciled with models that say something different. Anyone who tells you the Labrador Sea's future behavior is settled is overselling. What is not contested is the part that matters for anybody who has to go there. Less ice does not mean a safer sea, it means a different one, and in several respects a more dangerous one, and the reasons are mechanical rather than political. Sea ice damps waves. A surface covered in pack ice cannot build a sea, because the ice absorbs and scatters the energy the wind is trying to put into the water. Remove the ice, and you restore the fetch, the distance over which wind can work on open water, and a wind that used to blow across a frozen surface now blows across hundreds of kilometers of it. Same storms, bigger waves, in places and months that used to be protected. More open water and more meltwater also means more mobile ice of the dangerous kind. The bergs do not stop coming because the pack retreats. Retreating glaciers calve more of them, and open water lets them travel. 1,008 of them reached the shipping lanes in 2017. And an ice-free season that starts earlier and ends later is, from a commercial point of view, an invitation. Longer seasons mean more traffic, and more traffic in the shoulder months means vessels in this basin during periods when the atmospheric machinery is still fully operational. The storms are a winter phenomenon driven by the temperature contrast between continental air and the sea. Removing the ice does not remove that contrast. If anything, exposing warmer water to cold air increases the heat flux that feeds the storms. So the sea becomes navigable in months when it is still perfectly capable of building a bomb cyclone overhead, and the ships that go there will be operating further from help later in the year than anyone did before. There is one more consequence, and it lands on the people who have been reading this coast the longest. Along the Labrador shore, sea ice is forming later, breaking up earlier, and behaving less predictably than it did within living memory. For communities in Nunatsiavut that use the ice as a road, that is not an environmental abstraction. It is the loss of a transport network and a hunting platform. The observational system that Inuit knowledge represents has not failed. The reading of color, thickness, cracks, snow, and current is as accurate as it ever was. What has changed is that the accumulated baseline behind it, the sense of what this ice does in this month in this bay, is being outrun by the rate of change. The response has been to combine the two systems rather than replace one with the other. Smart Ice, based in Nain, puts sensors into the ice and combines the readings with satellite data and with observations from the people who actually travel on it. The Sikushutet Committee's 51 documented ice terms exist partly so that the vocabulary of a system in flux does not disappear along with the ice it describes. That is the same solution the Basques used: run with better instruments. Know what the environment is doing right now and retain the authority not to go. So put the whole machine together, because it has been assembled in front of you piece by piece and it fits. The geography sets the constraints. A deep basin several hundred kilometers wide with no shelter in the middle, bounded by a coast that ice closes and a coast that glaciers arm, with a 3,000-meter ice dome at its southern corner. The water supplies the fuel. Warm, salty Erminger water sitting under a cold surface layer, holding heat that Arctic air pulls out of it at hundreds of watts per square meter, so that storms are not visitors here but products. The weather converts the fuel into force. Explosive deepening overhead, a jet accelerating around Cape Farewell, wind against current over a shelf edge shortening and steepening the sea, and spray freezing high on the upper works, where the added weight hurts most. Human motives supply the exposure. Whale oil, cod, mail, sovereignty, war, gas, science, schedule. Nobody in this story went to the Labrador Sea for the view. They went because something valuable was there. And the thing that made it valuable was usually the same thing that made it dangerous. Technology changes what people attempt, and almost never changes the mechanism. A reinforced bow, a diesel engine, a radar set, a satellite beacon. Every one of them real, every one of them useful, and not one of them able to move Greenland, slow the current, or shorten the distance to Gander. Distance decides the outcome. That is the whole answer to the question this started with. The crews who died here mostly were not surprised by the weather. Several of them reported it accurately on time, to people who believed them and responded immediately. What killed them was that the correct information had nowhere useful to go, because the nearest help was hours or days away through the same conditions. And the history proves it repeats. A ship at anchor in 1565, dorymen in fog in the 1950s, 25 airmen on an ice cap in July, and 5 dead in the same place in November. 95 people 4 hours from anyone who could have reached them. Different centuries, different equipment, the same shape. Nothing in that system has been switched off. The Erminger water is still there. The cold air still comes off Canada in January. Cape Farewell has not moved. And the changes now underway are not dismantling the machine. They are opening the door to it for longer, to more people, in worse months, which is where it stands tonight. It is February, in the middle of the basin, in the dark. There are no ships in sight and no aircraft overhead. A meter-long cylinder rises through the last 100 meters of water, breaks the surface among the swells, lifts a short antenna, and transmits a temperature and salinity profile it recorded on the way up from 2,000 meters. The profile is almost a straight line. From the surface to 2,000 meters, the water is nearly the same, because it is the same water. What is down there now was up here a few days ago, and it is on its way into the deep Atlantic. The float finishes transmitting and sinks again, and somewhere along the same horizon, a set of navigation lights moves east across that position. A bulk carrier on a February heading through the Labrador Sea that no commercial master would have accepted 50 years ago, with the nearest helicopter about 600 kilometers away.